Diffusive gradients in thin films. The diffusive gradients in thin films (DGT) technique is an environmental chemistry technique for the detection of elements and compounds in aqueous environments, including natural waters, sediments, and soils. It is well suited to in situ detection of bioavailable toxic trace metal contaminants. The technique involves using a specially designed passive sampler. The element or compound passes through the membrane filter and diffusive gel and is assimilated by the binding gel in a rate-controlled manner. Post-deployment analysis of the binding gel can be used to determine the time-weighted average bulk solution concentration of the element or compound via a simple equation. History. The DGT technique was developed in 1994 by Hao Zheng and William Davison at the Lancaster Environment Centre of Lancaster University in the United Kingdom. The technique was first used to detect metal cations in marine environments using Chulex 100 as the binding agent. Further characterization of DGT, including the results of field deployments in the Menai Strait and the North Atlantic Ocean, was published in 1995. The technique was first tested in soils in 1998, with results demonstrating that kinetics of dissociation of labile species in the pore water soil solution could be determined via DGT. Since then, the DGT technique has been modified and expanded to include a significant number of elements and compounds, including cationic metals, nitrate, phosphate, and other oxyanions v. CRVI as CMO, SBW, antibiotics, bisphenols, and nanoparticles, and has even been modified for the GChemo. DGT Research Limited was established in July 1997 by the original developers of the technique, Profs. Davison and Zhang, and sells ready-made DGTR devices for water, soil, and sediment deployments to measure different analytes, as well as the component parts for self-assembly. The company holds the original patents for the device, and DGTR is a trademark. In 2014, a rival company, Easy Sensor, was set up by Prof. Shiming Ding and supplies devices that the company claims are analogous to the original DGTR products. The DGT device. The most commonly used DGT device is a plastic piston-type probe and comprises a cylindrical polycarbonate base and a tight-fitting circular cap with an opening DGT window. A binding gel, diffusive gel, and filter membrane are stacked onto the base, and the cap is used to seal the gel and filter layers inside. Dimensions of the gel layers vary depending on features of the environment, such as the flow rate of water being sampled. An example is an approximately 2 cm device diameter containing a 1 gel layer. Other commonly used probe configurations include those for deploying in sediments to measure solute mobilization with depth, and in planar form for measuring solute dynamics in the plant rhizosphere. Principles of operation. Deployment. DGT devices can be directly deployed in aqueous environmental media, including natural waters, sediments, and soils. In fast-flowing waters, the DGT device's face should be perpendicular to the direction of flow in order to ensure the diffusive boundary layer (DBL) is not affected by laminar flow. In slow-flowing or stagnant waters, such as in ponds or groundwater, deployment of DGT devices with different thicknesses of diffusive gel can allow for the determination of the DBL and a more accurate determination of bulk concentration. Modifications to the diffusive gel, e.g., increasing or decreasing the thickness, can also be undertaken to ensure low detection limits. Analysis of binding gels and chemical imaging. After the DGT devices/probes have been retrieved, the binding gels can be eluted using methods that depend on the target analyte and the DGT binding gel. For example, nitric acid can be used to elute most metal cations from Chulex 100 gels. NaOH can be used to elute most oxyanions from ZR oxide. Ding et al. 2010, 20,112,016, Sun et al. 2014. The eluent can then be quantitatively analyzed by a range of analytical techniques, including but not limited to IPMS, GFOS IPOS, Oz, UV vis spectroscopy or computer imaging densitometry. For chemical imaging and to obtain two-dimensional 2D sub-mm high-resolution distribution of analytes in heterogeneous environments, such as sediments and the rhizosphere, the retrieved gel strips can be analyzed by PIX or LA-ICP-MS after gel drying. The DGT equation. DGT is based on the application of Fick's law. Once the mass of an analyte has been determined, the time-averaged concentration of the analyte in the bulk, C, E, 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 D, G, E, T, \displaystyle C DGT, can be determined by application of the following equation: C, E, 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 D, G, E, T equals M, D, G, E, D, T, A, \displaystyle C DGT equals \frac and \delta GDT a backslash the 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 backslash where M display style M is the mass of the analyte on the resin. D, G, E, display style delta G to G is the thickness of the diffusive layer and filter membrane together. D, display style D is the diffusion coefficient of the analyte. T, display style T is the deployment time, and display style is the area of the DGT window. More elaborate analysis techniques may be required in cases where the ionic strength of the water is low and where significant organic matter is present.